All right, greetings for anyone who is out there. Greetings, Ulysses, how are you doing? If you hear any loud banging and noises in the background, well, I can just blame my kids for that because, well, they're kids and they're arguing about video games because why not, right? Ghost Killer, good to see you again. Now, I know some of you have probably missed all the fantastic cups that I've been bringing to class, so I have a different set that I'm going to be showing you guys. So here are some pints, so this is one of the many pints that I have. Don't really want to bring these to class. But the water is still delicious as ever. Alright, what's up, Laura? Rizbe, how you doing? I hope that you have been following our mantra, which is, what would Mr. Craig do, right? Alright, so we're just going to be talking about fractions. I know how much you guys love fractions, so let's start with the basics, and then let's see if we can build into some bigger and better and crazier things, maybe talking about some of the bigger rational expressions that we may have seen, like when we solved rational equations earlier this semester, when we have x's and x squared and all the other fun stuff in there. Okay, so, as you guys, of course we all know, fraction can look like this, a over b. Now, I know some of this is going to seem like you guys already know this, but this is going out to just any and all grade levels because I know that everybody is struggling, not being able to go to class, not being able to meet with their teachers, and I'm sure there are some people out there who may see this video who need help with fractions, even with the very basics here. So remember, what do we have here? I apologize. Here we go. My favorite colors right here. All right. So, of course, A is going to be what we call the numerator. And this guy down here, the B, is what we call the denominator. Now, I know sometimes we kind of get away with saying, oh, it's the top, it's the bottom. Let's make sure that we use the right words, numerator and denominator. Okay. And the easiest way to understand fractions, the most basic level, is how many parts out of a whole unit do you have? So if we take something like this. This is something that is divided into 3 parts, hopefully 3 equal parts. So 3 equal parts will make a whole unit. And if I were to, of course, just color in this part right here, we would say that's just 1 out of 3 parts that we have. Again, that's all that we really mean when we have fractions. I know it never happened in my class, but I've heard stories of teachers bringing in candy bars to help students understand the concept of fractions. That didn't happen for me, but it's it's very sad when you think about it. So if I have this fraction here, this big entire unit, it's made up of 8 equal pieces. And if I were to select these guys right here, then of course that means I have 5 out of 8 pieces selected, so you have 5/8. That's really all it is. So basics of fractions, we get that. And we also have this interesting concept too. And that is the concept of equivalent fractions. So here we have, again, something that is divided into thirds. And if I color in that same region, we can say that, yes, that is 1 out of 3 regions that we have colored. But if I come back in here and, let's still use the black here. If I divide these guys up again, like this, like a piece in the game of Trivial Pursuit, I didn't change the colored region at all. It's still the exact same. I didn't come up here and grab my red pen and start coloring more. What we see, though, is that now I have 2 out of 6 pieces that are shaded. And so these guys are equivalent fractions. And when we say equivalent, that means if you were to go onto the number line, here's 0, here's 1, and if you divide this equally into thirds, here is the fraction 1/3. Alternatively, if you divide the distance from 0 to 1 into 6 equal pieces. There's 1/6, and here is 2/6. So they occupy the exact same spot on the number line. So this is why we talk about equivalent fractions, and sometimes whenever you guys are taking a test, I take points off because you don't fully simplify a fraction. For example, if you say you get the answer 6/8. Okay, 6/8 it's a number, right? But we also know that we can rewrite this as 2 times 3 over 2 times 4, and since you have a common factor here, these factors of 2 can reduce, and we see that 6/8 is the same as 3/4. They occupy the exact same spot on the number line. Now, again, I know how a lot of students don't believe me. Why should you? Let's go to the calculator, right? We all believe this. If I type 6 divided by 8, I get 0.75. And you see that if I do 3 divided by 4, I also get 0.75. So as a decimal, these guys are exactly the same. And I know right now some of you are thinking, well, then why don't we just do everything in decimals? Well, the easy example I do is, how about 2/7? If you want to look at that guy as a decimal, that is approximately 0.285714, but those six digits keep repeating. And if you want to do this as a decimal, you have to make some kind of choice. Do you round to the nearest hundredth, the nearest thousandth, or do you go for full accuracy and say 0.285714 with a fraction bar over it, with a repeating bar? But you don't want to do that because it's not a very portable number. It's hard to take it from one spot to another spot. But by saying the fraction 2/7, it's really easy. And we're going to be seeing those guys today in some of the examples where going to the decimal is not really the best thing for us. But above all, I need you guys to understand that fractions are just numbers. That's all they are. I don't want you to think there's something mystical that we can't do, or you're thinking, well, back when I was younger, they were impossible, they were the hardest things ever. No. You can do it. I'm here, you're here, and I hope you have something to write with, something to write on, like a piece of paper, not your arm, and we can do some fun examples. Well, I say fun, but you know me. You know my idea of fun is a little bit different than yours. Hopefully your idea of fun is washing your hands for at least 20 seconds with soap and warm water, right? Don't touch people. Stay away from people. Keep your distance. There we go. I've said it. Again, what would Mr. Craig do? Wash your hands. All right. So you threw me off. Oh, goodness. And there's my precious dog who just scared off a delivery person. Yeah. No, you got him. You got him, girl. Who knows? She might even pop into the screen. Oh, that vicious delivery person. Who knows what they were delivering? All right. Crazy. All right, so I think I'm going to start off here, and let's just talk about what could be the easiest guy, is that in order to add and subtract, okay, we must have common denominators. And we know that as long as the denominators are the same, life can be pretty simple. And having the same denominators just means that we're looking at everything on the same level. Oh, look at that. Drea84, how are you doing? Although, guys don't know that, I'm just messing with her. That should be my sister-in-law. Hope you're having fun up there. Thank you for dropping by and doing fractions, because that's what you want to do on a Friday afternoon, right? Later on, you guys can go to happy hour and discuss what we've learned here today. Unless, of course, you are like in first or second grade, and then maybe your happy hour is just a juice box and some potato chips. Classic. All right, so if I'm going to add fractions like 1/4 plus 2/4, we do want to make sure that we recognize that these guys have the same denominator. And as long as these denominators are the same, you keep that denominator. So you keep that denominator and you just combine those numerators. And so you get 3 over 4. One of the things I see a lot of students do is they try to add the denominators as well, which to me has never really made a lot of sense. You can't really do that. Ergomen, nice to have you here. And if you think about what this means, think about these fractions, think about what you're trying to put together. Okay, so on one side you have 1 out of 4 pieces colored. But then you've got the 2 over 4, so that means you are coloring in 2 out of these 4 pieces. And so you can see that what we have shaded in is 3 out of 4 pieces. That's all it means. Don't ever add the denominators. I don't think there's ever a place where you're going to sit there and say, let me add the denominators. No. And one of the issues that we run into later on is if I take something like this. If I take 1 over 6, and I want to add that to, let's say, I just lost my mind. If I want to add this to 5 over 14. See, right now I can't really compare these guys because they're not on the same level. They don't have the same denominator. So you can't really say, oh, one of these guys is more than the other. And you can't make that comparison until the denominators are the same. It's just like if I said, I've got 2 coins. How much money is that? Well, you don't really know. And the thing is, like when it comes to money, if we take, let's say, a dime plus a quarter. A dime is 1/10 of a dollar, and a quarter is 1/4 of a dollar. Now, when I look at it like fractions, it may be hard to understand which one is which one is stronger, which one is worth more money, until we put these guys over the same denominator. So, over the same denominator, of course, we talk about money. Money always makes sense to us, I hope. We do something like this. Now, I'm not saying that 100 is the least common denominator, but it is a common denominator. Okay, you say I went fuzzy. Am I still fuzzy, or can you still see? Hopefully you can still see what I'm doing here with the math. If something goes wrong, let me know and I'll do my best to fix it. Still trying to figure out all the ins and outs of everything here. Oh, cool beans. So, you know that with a dime means 10 cents. If you've been in this country long enough, you know that's what it means, and a quarter means 25 cents. So when we look at it like this, it's easy to compare that 25 cents is more than 10 cents, and you know that a quarter is more than a dime, not just because of the size of the coins, which you can't always trust that, but because we have experience, real-world experience that tells us that. And we know that if we add these guys, once they are out of the same denominator, out of parts of 100, we know that we have 35 cents. Like we know that if I take a dime and a quarter, I get 35 cents. But again, we can't really compare these guys until we have the same denominator. Now, what we're going to see here in a little bit is how do we get the same denominator? Because that seems to be one of the biggest questions that students have is, well, how do you find the common denominator? We're going to get there. Trust me. It's not going to be as bad as you think it is, and we're going to try to make it as quick and easy, as simple as possible. All right. So just to make sure that we are okay with adding and subtracting, if I take 5 over 14 minus 3 over 14, as long as those denominators are the same, we can easily add and subtract. Well, these denominators are the same, so I'm looking at a denominator of 14, and I'm just going to do 5 minus 3, and we get 2. Now, we can't stop here because we have to make sure that we simplify our fractions. And when I say simplify, I mean put it into lowest terms. Okay? When I look at 2 and 14, I need to see if there's a common factor. Now, remember, when we use the word factor, we're talking about a piece of a product, a piece of the multiplication problem. So when I look at 2 and 14, is there a number that can divide into those guys evenly? Well, I know that I can rewrite this. I can rewrite 2 as 1 times 2, which you might say is overkill, but just go with me here. And 14 is 2 times 7. So we factor these guys down all the way, and we see here they have a common factor of 2, right? And so I'm going to reduce those guys away, and I don't want to say cancel them out. I talked about that on the last time I streamed. We were talking about exponents. We say they reduce away, and we get 1 over 7. Now, Ghost Killer, I see that you say in the chat divide by 2, and I'm going to say no. They can both be divided by 2, but we are not taking the fraction 2 over 14 and dividing it by 2, because that would change the problem. We're not going to introduce anything new that's going to change what this expression means. 2 over 14 is the same as 1 over 7. But if I just randomly say, hey, divide this by 2, that changes a number. Almost any number that you say divide by 2 is going to change it, except for 0. Of course, you could divide 0 by anything. It's still going to be 0, unless you try to divide 0 by 0. And please don't do that. If you start dividing by 0, the math police are going to come knocking on your door, and they're going to say, hey, we got a report that you were dividing by 0. We need to come in and see what's going on. Of course, what happens when you divide by 0? Anybody? Come on. My peeps in the chat, you in my class, tell me what happens. When you divide by 0, what do you get? Or are you going to make me sing the song? You want me to sing the song? I know you do. I'll wait to see if you guys respond. So the 2's reduce, because what's really going on is that we're saying that 2 over 2 is equal to 1. And so what you're really doing is that you are dividing out a form of 1, which doesn't change anything. Oh, you guys really want me to sing the song, right? Okay, so let me go ahead and do this for you. I'm going to take my red pen for emphasis here. So here are some things for us to know. If I have 0 divided by any number, this is going to equal 0, provided that that denominator does not equal 0. Okay? Another thing, if you take a number divided by itself, you get 1. And again, this is under the provision that that denominator is not 0. It's like, why do we have to keep making these provisions for when the denominator is not 0? Well, here's why. When you divide by 0, the expression is undefined. Yes, undefined. Remember the song that we did? When 0 is under the line, the expression is undefined. How quickly you guys forget. See, spring break was just a horrible idea. I'm going to see if I can talk to the chancellor and see if we can just abolish spring break forever, and we never take breaks from school. You'll always be in my class forever. Right, so you don't divide by 0, and you're probably going, why is that undefined? Remember what we said about the denominator a little while ago. The denominator tells you how many equal parts make up a whole unit. So when I have something like this, if I say 1 over 4, that means that you have taken an entire, complete, whole something, and you have divided it into 4 equal parts. And with those 4 equal parts, you are taking one of those pieces, right? If I were to do something like 1/2, that means I'm taking something, I'm dividing it into 2 equal parts, and I am taking one of those parts. So you actually have something, right? Even if I do something like 1 over 1, 1 over 1 means that one whole unit is divided into one part, one equal part. And if you take that, you actually take the whole thing. But what if I try to say this? If I try to say 1 over 0, that means that you're trying to take a shape, maybe like a square or circle, and you're trying to divide that into 0 equal parts. How do you take a piece of paper and divide this into 0 equal parts? Now, right now, this is just one part. I could cut it down the middle, and I would have 2 equal parts. I could keep cutting it into smaller and smaller pieces as long as they were equal parts, and that would then be my denominator. But Having a denominator of 0, we can't do that. And so what we say is that we just call this undefined. And this comes back later on. We talk about rational expressions, rational equations that we're trying to solve, and we have to pay attention to make sure that the denominator never becomes 0. Because if it does, then we end up talking about restricted values. So, depending on what your level is here, if I were to take a bigger, nastier looking rational expression like this, let's say 2 over x plus 5. Since x is a variable, it can represent any number that you want, almost. See, the caveat here is that all the stuff that we talked about above, this denominator, x plus 5, is never allowed to equal 0. So you can plug in any value of x that you want to, as long as it doesn't make the denominator equal 0. So you can solve this just like you would any other normal equation. And if you subtract 5 on both sides, that means that for x plus 5 to not equal 0, that means that x is not allowed to equal negative 5. And so this negative 5 here is what we call a restricted value. And again, that's stuff that we've gotten into in our class, and if you haven't gotten there, if you were just like starting out early on in the fractions, you will get there. And so what this says is that as long as I plug in any value of x that's not negative 5, I'm going to be okay here. It doesn't mean it's going to be a nice, pretty number. It just means that I actually get something. Even if I plug in 0, if I plug in 0 for x, so let's write this. If x were to equal 0, what happens? Well, you would have 2 over 0 plus 5, which is just 2 over 5. That's no problem. That's just a fraction. If I say x is equal to 95, then we have 2 over 95 plus 5, so that's 2 over 100, and I can't help myself, I've got to simplify this, and that reduces to 1 over 50. So you can plug in any number you want to, but let's see what happens if I plug in negative 5. So if x were to equal negative 5, you end up with 2 over negative 5 plus 5, which becomes 2 over 0, which is undefined. And so that's why we have to remove x equals negative 5 from the entire discussion for this particular expression. Because if I plug it in, I get an undefined expression. And it kind of ruins everything. Which is why at the beginning of the semester when we had rational equations, I said make sure you identify the restricted values. Because if you get a solution that matches up with the restricted value, you have to remove it from contention, and it's called an extraneous solution. But that's a little bit more than what we're getting into for the video right now. And I hope over these coming 3 weeks before classes finally resume, we're going to spend these 3 weeks and we keep making videos and keep streaming all of the stuff that we've done in the first half of the semester so that we can stay caught up, we can stay fresh, and then we can hit the second half of the semester with a running start. All right. So I do want to talk to you guys about equivalent fractions. And like we were mentioning before, an equivalent fraction just means it occupies the exact same spot on the number line, but it just looks a little bit different. That's all. For example, if I take the fraction 1/2, maybe for whatever reason, I need to see this as 5 over 10. Or I could see this as 3 over 6. There are an infinite number of possibilities here for the fraction 1/2. I could say 71 over 142. All of these guys mean the exact same number, and they occupy the exact same spot on the number line. Now, how do we get these equivalent fractions? It all comes down to the concept of a form of 1. So you're going to hear me say that a lot. So let me write that out so you understand what I'm saying. A form of the number 1. So I can take 1/2 and I can multiply this times a form of 1. A form of 1 being something like 3/3. Like we showed on the previous page, as long as you are dividing a number by itself, that's going to be equal to 1. And if I multiply times 1, nothing changes. That's the great thing about 1. It's what we call the multiplicative identity. You can take any number that you want to and multiply it times 1, and you get the same result. It's the same thing, the same place on the number line. It might look different, but it's still the same. Now, when you multiply, all you do is multiply straight across. So you multiply 1 times 3, 2 times 3, and you get the fraction 3/6. That's all. And if we go back to our diagrams, you can see why this is the way it is. Oh, did not realize that my dog was right underneath my seat. Sorry about that. So if I do this, here is the fraction 1/2. Multiplying times 3/3 means that I am basically dividing this into thirds like that. And so you see that now 3 out of 6 places are colored. It's the same fraction. That's all. So let's do more with multiple. Well, let's stick with this. So if I have 3/5, and I want to make an equivalent fraction. Suppose I want to make this into something that is the denominator over 20. In order to figure out how to get that conversion going, you've got to figure out what would you multiply 5 times to get 20. And so we understand if I do 5 times 4, I'm going to get 20. Then I can easily make this conversion. So off to the side here, I can take 3/5 and multiply it times, no, don't say multiply times 4. If you multiply times 4, that changes the problem. We're multiplying times 4/4. Because 4/4 is still 1, and again, as long as I multiply something times 1, it doesn't change its value. So now I can get my denominator of 20, and my numerator just follows along. 3 times 4 is 12. That's all we have to do. If I were to take the fraction 2/7, and I want this to now have a denominator of 42, I really just need to figure out basically how many times does 7 go into 42. We know that that is 6. Just do some simple division. So my workout here off to the side, I guess I should go ahead and fill this in here. There we go. So I'm just taking 2/7. I know that I need to get a denominator of 42 because that's what the example is saying. I'm going to multiply both the denominator and the numerator by 6. Again, the reason I use 6/6 is because that's just equal to 1. Again, if I multiply times 1, it doesn't change everything. Yes, Ulysses 6/6. And when I do this multiplication, my denominator is going to be 42, and my numerator is 12. Okay? And no, that was not intentional that they were both going to be 12. Not every answer is going to be 12, trust me. Alright, so what if I do this? I'm going to say 4/9, and I want to convert this into something that is over 72. So, what's that numerator going to be? Let's do some scratch work over here to the side. We need to find that missing factor. It's all about the missing factor. Yes, Kevin has figured out the missing factor, which is 8. But I can't just multiply the denominator times 8. That totally changes the problem. However, if I kind of create this balance in the numerator with 8, then it's going to be equal to 1, and I'm not changing the problem. So I get my denominator of 72, and my numerator, 4 times 8, is 32. So you see, we haven't done anything crazy, anything special. You don't even really need a calculator for what we're doing here. We just need to know how to add, subtract, multiply, and divide, and you're going to be fine. So as long as you know your multiplication chart, like that one they did back in 3rd grade or whatever, the 12 by 12, if you've got that memorized, there's nothing that's going to stop you here in math. Nothing. So here's my denominator of 32. Now, why are we getting equivalent fractions? Well, that's so that we can add fractions that don't have the same denominator. Of course, that opens up the big conversation about how do you find a common denominator? What is a common denominator? We're going to get that here in just a moment. What we're doing is that we're making these fractions become, well, they make them look bigger because we're increasing the denominator. But as long as you increase the numerator at by the same factor, it's going to be the same fraction, the same value, the same number. But let's also talk about going the other way. We were seeing this earlier. If I were to take 25 over 35, and I want to reduce this, I want to write it in lowest terms, I need to identify what is the greatest common factor. Or really, you don't even have to go for the greatest common factor. Just find a common factor. Just start making these numbers smaller and smaller so that you can get to your final reduced form. Again, this requires you to have working knowledge of that 12 by 12 multiplication grid. If I rewrite this, I can see that there's a common factor because 25 factors as 5 times 5 and 35 factors as 5 times 7. As long as we can find a common factor between the numerator and denominator, I can reduce, I can simplify. So I see that I have 5s that are common. Now, whenever you reduce, you have to make sure that you are reducing one in the numerator and one in the denominator. Never, ever, ever cancel side to side. That is bad, bad, bad. So I'm going to reduce this 5 with that 5. And that's going to give me the fraction 5 over 7. Okay. Now, really what I'm doing here is I almost feel like I'm skipping a step. If you understand that and you're good with that, then we're fine. But so that you have a deeper understanding of what's going on, let's make sure that we see this fraction for what it is. When I say 25 over 35, and I break it down, it's 5 times 5 over 5 times 7. What I'm really saying is that this is 5 over 5 times 5 over 7. And you see how this guy shows up right here. 5 over 5 is equal to 1. And we just got done saying that 1 is the multiplicative identity. And if I multiply times 1, it doesn't change anything. Also, if you divide by 1, it doesn't change anything. So having that factor of 1 there doesn't really matter. It doesn't change anything, doesn't affect anything. You know what? For all you guys in the stream that are one of my students, I'm going to multiply your grades by 1. You're welcome. Just make sure that you remember that on the instructor evaluations later on this semester. I multiplied your grade times 1. I'm so nice. All right, so let's take 14 over 42. Can we find a factor that's common between 14 and 42? Now notice I said factor. I didn't say greatest common factor because it doesn't really matter. If you don't see what the greatest common factor is at the very beginning, that's fine. You can break this guy down piece by piece. So I hope that you guys can see that both of these numbers are even. So at the very least, I can write this as 2 times 7 and 2 times 21 to get things rolling. And here, the 2 over 2 is equal to a factor of 1. And so now I get 7 over 21. Yes, Ulysses, that is one way to break it down, but you got to find out there's still going to be more work for you. Even here, I've got 7 over 21. And you guys see there's a common factor here of 7. I can say this is 7 over 3 times 7. And again, I have these guys being the same. And just like the 2 over 2 is a factor of 1, 7 over 7 is a factor of 1. But you got to be careful. If you're not, you're just going to say that the answer is 3. But the answer is not. What we have to remember is that you can never leave a numerator empty. Denominators don't have to be written. Okay? Just like if we were talking about how old you are, and you say you're 25. You don't say 25 over 1 because it doesn't make any sense. You don't need to say that. It's irrelevant. But here, this 3 was my denominator, and I can't just leave it like that. I need to make sure he's in the denominator, and what's left in the numerator is a factor of 1. See, I didn't write 7 as 1 times 7, but I could have. And here is our final result. So 14 over 42 is the same thing as 1/3. Now you notice that I did this in two different steps. I didn't have to. I could have done it in one step if I had only recognized that I've got 1 times 14. 42 is 3 times 14. And here is your greatest common factor, your GCF, that reduces, and you'd be left with 1 over 3. You still get the same thing, right? Another way of doing this, another way of showing the steps, is that you can do this. Like I did up here, I divided both of these guys by 2. And notice what I'm doing here is I'm dividing by 2 over 2, like this. So that leads us to 7 over 21. And then in the next step, I divided by 7 over 7. Again, you're dividing by something that is a form of 1, so it doesn't change the meaning, it just changes the way that it looks. So no matter how you slice this, that fraction is going to reduce to 1/3. What do you think? Cool beans? Always cool beans. All right. All right. Well, you're welcome. Glad you guys are getting this. This is fun. Until we make it worse, right? So when it comes to multiplying, now I don't know if I've said this before, but multiplying is one of my absolute favorite things to do. Because with multiplying, you don't need things to be alike. You don't need common denominators. You just multiply. You don't have to have like terms, just multiply. So the trick here, not really a trick, but the way that this works is that when you multiply, you just multiply straight across. Don't do anything that sounds remotely like the phrase cross multiply. Don't do it. Stop saying that. Please stop. Do not say cross multiply. Because students think cross multiply and then they don't multiply correctly. When you multiply fractions, you just go straight across. You multiply these guys right here. And so you have the product A times C, whatever that happens to be. And then you multiply these denominators, B times D. That's it. That's all. That's all you have to do. Now, sometimes it gets a little bit more complicated when we try to simplify it in the middle, but really, that's all you do to multiply fractions. So if I take 1/2 and I multiply that times 1/3, according to what I'm saying up here, you multiply 1 times 1 to get 1, you multiply 2 times 3 to get 6. That's all. That is all that you're doing. Now here's another way of saying this. Sometimes we say 1/2 of 1/3. We remember word problems a long time ago. A lot of times when we hear the word of, we tend to connect that with the operation of multiplication. So I want you to see in a picture why 1/2 times 1/3 is 1 over 6. And it's all going to come down to this phrasing here, that we're talking about 1/2 of 1/3. Okay? So let me draw my nice little diagram over here. And we're going to divide this into thirds. Okay? So right now I'm talking about the fraction 1/3. So I'm taking 1/3 of this. But now we want to do half of 1/3, which means we're now cutting all of this in half, and I'm going to do 1 out of 2 of these. So I already have 1 out of 3, and now of the 1 out of 3, I'm going to do 1 out of 2 of those guys. And so you see the piece that's really colored in is this guy right here. But for the entire diagram, we have colored in 1 out of 6 pieces. So that's why the rule for multiplication works when it comes to fractions. So, if I take 2/3 times 5/7, just do what we did above. Multiply straight across. So 2 times 5 is 10, 3 times 7 is 21. Now what you would do here is to see, oh, does this simplify? Can I reduce 10 over 21? But the answer is no. When you see how these guys are written, what their factors are made up of, let's look at that step before we actually multiplied. We had 2 times 5 over 3 times 7. These guys are all prime numbers. So if you're trying to reduce this, you have to have a factor that's common for all these guys. But there's nothing common. This is the only 2, that's the only 5, the only 3, and the only 7. So no matter how you slice it, this is all you have, 10 over 21. And you can't reduce that. However, let's take this. Let's do 4 over 5 times 3 over 2. So again, let's just multiply straight across. 4 times 3 is 12. 5 times 2 is 10. Yes, we multiplied. Huzzah! But now we have to reduce this. Or at least see if it can reduce. If I look at 12 and 10, is there a common factor? Yes, these guys are both even. And this is one of the things I want you to understand. If both of your numbers are even, you know that you at least have 2 as a common factor. So even if you can't see the greatest common factor for the whole thing, like on this, one of the last problems we did right here, even if I didn't know that 14 was my greatest common factor, I can at least start small. I can reduce out the factors of 2, and it gets back down to numbers that maybe I'm more familiar with, I'm more comfortable with, and I can see how it simplifies after that. Okay? You don't always have to go big at the very beginning. Take it in smaller steps if you need to. Okay? So with 12 over 10, there's a common factor of 2, so I can reduce both the numerator and the denominator by 2, and I'm left with the fraction 6 over 5. Now, depending on what level you're at in math, you may or may not want to rewrite this. You may have teachers that say fractions like these are unacceptable, and I disagree. This is an improper fraction, and it's an improper fraction just because of the numerator. So with an improper fraction, this is a fraction that's of the form a over b, where the value of the numerator is greater than or equal to the denominator. So basically what that means for an improper fraction is that you have, like in this diagram, you would have filled up the entire diagram and maybe a little bit more. Like this, 6 over 5. That means out of 5 pieces that make up a whole unit, you are taking 6 of them, which means you have enough for 1 complete unit, and then you've got a fraction left over. And so that's something that maybe in another stream I'd get into when we start talking about mixed numbers. But again, on the college algebra side of things, we tend to not do that. We stick with improper fractions. 6 over 5 is fine. The only thing I say to my students is that I don't care how your fraction, how your answer looks, as long as it's reduced, as long as it's simplified. And this guy is. No problem. But there's something else that we could have done before I multiplied to get 12 over 10. So let's look at this guy one more time. 4 over 5 times 3 over 2. If I don't multiply, but I keep things factored in the numerator and the denominator like this, I now have a single unit written for my fraction, and I'm trying to see if there are any factors that are common that I can reduce. 3 can't reduce with the 5 or the 2, right? Because you have to reduce something in the numerator with something in the denominator. But what about 4? 4 has nothing in common with the 5, but it does have something in common with the 2. In fact, they have a common factor of 2. So what we can do is that we can divide the 2 by 2 to give us 1. We divide 4 by the same value of 2 to get 2. And so you've effectively reduced out the common factor of 2, and we are left with 2 times 3, which is 6, over 5 times 1, which is 5. Still get the same answer. Now this is incredibly useful when the numbers start to get bigger and bigger, right? So if I take 24 over 25 times 35 over 36. Now, what you probably don't want to do is that you don't actually want to take 24 and 35 and multiply them together. That just doesn't sound like fun to me to get 840, right? And you don't want to do 25 times 36 and get 900. You could, but why do you want to go to such big numbers? You don't have to do that. You can keep the numbers small and keep them in your favor. While the numbers are still small, look for the common factors. Does 25 have anything in common with the 24? No. But if you look at 24 and 36, they do have common factors. They have something in common. The greatest common factor for these guys is 12. Now, let me do this. Let me rewrite the 36 to say 3 times 12. Maybe it would be better if you saw it like that. And the 24, I can scratch that out and write that as 2 times 12. And maybe by writing it out like that, you see, okay, those 12s get to reduce because 12 divided by 12 gives you 1. Well, that's good. I've got a lot smaller. The numbers are already smaller. That's good. What about anything else? 2 and 25 doesn't reduce. 2 and 3 doesn't reduce. Okay. What about 35? 35 and 25 have a common factor of 5, so we can reduce that by that common factor. But first, let's rewrite it. 35 is 5 times 7, and 25 is 5 times 5. Okay, and so by writing it like this, we see there's a common factor of 5 that can reduce, so those guys are now gone. And let's clean up our fraction to see what is left. So we have a 2 that's left over, and we also have a factor of 7. In the denominator, there's a factor of 5 and a factor of 3. These are the only factors that are left over, and that gives me 14 over 15. And that's it. 14 over 15 can't reduce. You think about what 14 is made up of, 2 and 7. They have nothing in common with 5 and 3. So that's it. Now, let's go back to what I said before. If you don't reduce before you multiply, you're going to get larger numbers. Okay? So 24 times 35 is 840. And 25 times 36 is 900. So you could have taken that route. And then from here, you're still going to have to simplify. Well, one of the things that stands out to me immediately is the fact that they both end in a 0, which means they both have a common factor of 10. So the cheap, easy way is to just kind of knock off the zeros like that. That is us effectively dividing both of these guys by 10. And so now we have 84 over 90. If you can't see what the common factor is right away, like the greatest common factor, go small. We see that both of these numbers are even, so we can at least reduce by 2, and maybe that puts us in a better position. So 84 divided by 2 is 42. 90 divided by 2 is 45. Can things be reduced more? And the answer is yes. We know that we can't reduce these guys by 2 anymore, but stick with your prime numbers. After 2 comes 3. To see if 3 is a factor of this, the trick is to add these numbers, and if the sum of the digits is divisible by 3, the original number is divisible by 3. So 4 plus 2 is 6. Since 3 goes into 6, 3 can go into 42. 4 plus 5 is 9, so 3 goes into 9, which means 3 goes into 45. So cool. We can reduce each of these guys by a factor of 3. 42 divided by 3 is 14, and 45 divided by 3 is 15. And there we go. Now, I don't know about you, but I liked what happened up here better. I never had to go to large numbers. The largest number I ever saw up here was 36, which is easy enough for me to handle. By going to the large numbers, it took more steps, it took me out of my wheelhouse, and I wasn't really that comfortable. But if I keep the numbers nice and small, then everything's going to be fine. So that's what I like to do. Trying to make my life easier. So it was multiplying. And the good news for us is that when it comes to dividing fractions, it's just as easy. Actually, the silly thing is, the way that we were taught to divide fractions is to turn it into a multiplication problem. So if you are dividing a fraction by a fraction, you keep this guy, the first one, you keep it exactly as it is, but then you turn this division into multiplication, and this fraction that you were dividing by, you flip it over, and you multiply by what is called the reciprocal. Remember, for a fraction, a reciprocal is just taking the fraction, flipping it over. That's it. And of course, once you turn this into a multiplication problem, it's just like everything else that we've already done. So if I were to take 2/7 divided by 1/2, the best way for me to do this is to turn the division into multiplication. But again, you keep the first fraction the same, and you turn division into multiplication, and you take this fraction right here, and you multiply times its reciprocal, which in this case is 2/1. And now that we have a multiplication problem, we just multiply straight across. So we get 4/7. Again, you want to try to reduce this if possible, but you can't. So we're done. Almost too easy, right? So you're probably thinking, we just turn it into multiplication and that's it? Yeah. Now there is another way to do it, and that requires us talking about common denominators. But let's not get there just yet. Let's take 3/5 divided by 9/10. So as we said before, for division you keep the first guy exactly the same, and you're going to take this division. The division becomes multiplication, and we're going to take this piece right here and turn it into his reciprocal, 10/9. And now it's a multiplication problem, so you just multiply straight across. But you could also look to see if we can reduce before we multiply. So, can 3 reduce with the 5? No. But can 3 reduce with the denominator of 9 over here? And the answer is yes. So, I'm just going to rewrite this. That way you can clearly see what we're doing here in each step. Okay, so we're saying that 3 and 9 have a common factor of 3, so 3 goes into 3 one time, 3 goes into 9 3 times. And then when we come to the 5 and the 10, these guys have a common factor of 5, so 5 goes into here once, and 5 goes into the 10 twice. Now I know a lot of times you see that I'm canceling and they're not necessarily on top of each other, but it's kind of like crossways like this. Don't let that throw you off at all. Remember, with multiplication, the order doesn't matter. So I could just as easily seen this as 3 times 10 over 9 times 5. And here, 3 goes into 3 once, into 9 3 times. 5 goes into 10 twice, and into 5 once. No matter how you do it, you still end up with the same answer, which is 2/3. That's it. Alright, so here's what you guys have all been waiting for. This is why you all showed up. You wanted to see, how do we deal with adding fractions when the denominators are not the same? Okay. So if I take 1/10 plus 2/15. Jade, so in terms of the homework in my math lab. If you want to keep working on that, you can. Since I'm in the process of converting the rest of the semester into online, I'm going to be creating modules in my math lab. I'm going to be sending you an email about that in the coming days, maybe tomorrow. It's going to kind of outline the new due dates and how we're going to finish the rest of this semester. If you look at my math lab, you'll see that some of the due dates have already been changed. Of course, our next test is not going to be on Tuesday because we're not going to be in school. But if you want to get ahead, if you want to watch videos, I encourage you to do that. Excuse me, of course, none of that is going to be mandatory just yet, but I will be recording some new videos and having some virtual office hours for you guys so that we can have these conversations, and maybe you guys can even pop up, whether I'm using Zoom or Skype. I'm not exactly sure what the best format is going to be for that. But right now, just kind of take it easy. Make sure that you understand all of the stuff that we've covered up to this point. That's what you can be doing over these next few weeks. Okay, back to this question here. We cannot add these guys right now because they don't have the same denominator. So we have to get a common denominator, which requires us finding the least common multiple of the denominators. All right, so there are a bunch of different ways we have of doing that. Let me show you one way, and I'm going to show you another way that I think might be a little bit easier. So if you're trying to find the least common multiple, not even just in a fraction scenario, but any time at all, we can do this little number over here. Take the two numbers that we're concerned with and start finding numbers that can divide into those guys. So right now, we know that 5 goes into both of these. So I can write a 5 out here, and I'm going to divide each of these guys by 5. That gives me a 2. It gives me 3. Now, there aren't any other common factors here, but here's what I'm going to do. I'm going to keep dividing numbers until I just have ones left. So, for example, I'm going to divide by 2. 2 goes into 2 one time. 2 does not go into 3 evenly, so leave the 3 as it is. Now, once you have a 1, don't worry about that guy. Worry about the 3. Divide these guys by 3. Now, 3 doesn't go into 1, so don't worry about that. Just leave it as 1. 3 goes into 3 one time. Once you get to this situation where everything here is a 1, these numbers that you have on the outside here will form your common multiple. Please make sure you understand that a common multiple is not the same as a common factor. Right? So like up here when I have 10 and 15, and I said 5 is a common factor, okay, that's not the common denominator. This is just a number that goes into both of those. When I'm talking about a common multiple, I'm talking about a number that these two numbers can both go into. If I take this right here, that tells me that my least common denominator is going to be the product of 5, 2, and 3. So my least common multiple is 30. So what I need to do here is, in this problem, I need to somehow convert these guys like we did earlier. So these are both fractions with a denominator of 30. Now don't say that we can't get there. Of course we can get there, because if you look at this, 10 goes into 30 evenly, 15 goes into 30 evenly. So it's a common multiple, so we can get these equivalent fractions. So, you know what I just said? I said that 10 goes into 30 evenly. Well, how many times? You know what? If you just want to shout it out, shout it to your cat, that works too. So 10 goes into 30 3 times, so what's missing here is the factor of 3. Now, I can't just put that in the denominator because it would change the fraction. It changes the number. So instead, we put it in both the numerator and denominator because what is 3 over 3? It's a form of 1. So as long as I multiply times 1, nothing changes. So 1 times 3 is 3. So I am claiming that 1 over 10 is the same as 3 over 30. Well, what about the 15? How many times does 15 go into 30? 15 goes into 30 twice. So what's missing here is that common factor of 2. Okay? So multiply both the numerator and denominator by 2. 2 times 2 is going to give us 4. And so now we have these equivalent fractions They have the same denominator, and so now these guys can be added. But remember, keep the denominator the same, and you just combine the numerators like that. 7 over 30. That's all you have to do. But I think the biggest trick, the biggest hurdle that students have here is, how do you even come up with the 30? How do we find the 30? It just seems like magic. Well, again, you can find the common multiple by doing this. That's also a way to find the common denominator, because when I say LCD, I'm really saying the LCM of the denominators. Here is another way of working it out. So let's take 1 over 10 plus 2 over 15. And here's what I want you to do. Now this is going to require us to understand the common, or the concept of the common factor. What's the common factor for both 10 and 15? The common factor is 5. So I'm going to rewrite this with a 5. So 10 factors is 5 times 2. 15 factors is 5 times 3. The whole idea about a common denominator is to make sure that the numbers in the denominators are the same, which basically means they have to have the exact same factorization, the same factors. So right now, 5 is the same for both of these. And so what we have to do is put in the missing factors. So I look here, this guy has a factor of 2, this one has a factor of 3. But we need everybody to be the same. So to make sure that everybody is the same, I'm going to put this factor of 3 over here. So see, now this denominator is not going to be jealous of this guy. See, the second denominator had a 3, and now he has a 3. But you got to make sure you pay for that, so you got to multiply the numerator times 3 as well. But now you look at the second fraction, now he's going to be upset, because the first fraction has a factor he doesn't have. So the factor that he is missing is the factor of 2. Remember what I said about how multiplication is great because the order doesn't matter? You've got 5, 2, 3. Each of the denominators have the exact same factors. So these are the same denominators. So we can now rewrite this. 3 over, no matter how you look at this is 10 times 3 or 15 times 2. That still gives us 30. So you work out these fractions and their equivalencies, and you still get 7 over 30. And so we don't have to worry so much about going through finding the LCM like that. Look at the factors. If you can find those common factors, you can make very quick work of these problems. Okay, so let's try another one. All right, so now I'm going to do this one, and then I'm going to give one for you guys to do and see what you do with it. I'll take 7 over 32 plus 9 over 40. Now if I ask you to find the common denominator, it might be kind of rough, especially once the denominators start to get kind of large. But think about what we just did in the last problem. If you can identify the greatest common factor between these two guys, it's going to make the rest of the problem pretty easy. So the GCF for 32 and 40 is 8. So 32 is 8 times 4, and 40 is 8 times 5. So again, what I'm doing is I'm rewriting the denominators to look at them purely from the standpoint of their factors. And right now, the 8s are common. So I don't need to worry about the 8s when I'm trying to get a common denominator. It's the 4 and the 5 that I have to worry about. So if we look here, we see that this guy's missing a factor of 5 that the other guy has. So naturally, he's jealous. So put the factor of 5 here, and also put that in the numerator because we can't neglect that. And so now when we look at this, they both have 8, they both have 5. But we see that that second fraction is missing a factor that the first one has, he's missing the factor of 4. So I put in the missing factor in both the denominator and the numerator. Okay, so all of this stuff right here, 8 times 4 times 5, is equal to 160. Over here, 8 times 5 times 4 is also equal to 160. Now, we didn't find 160 as the common denominator at the very beginning because we were just looking at the factors. There's no need for us to look at the big numbers. There's no sense in that. Keep things small, keep it manageable. And once we do this, we know now by doing either whether you do 32 times 5 or 40 times 4, you get 160. You work on the numerators here. So 7 times 5 is 35. Over here, we're still over 160, and 9 times 4 is 36. Same denominator. These guys are on equal footing. So one of these fractions is accounting for 35 out of 160 pieces. This is 36 out of 160. When you combine these, we get 71 over 160. You can try to reduce this. Unfortunately, 71 is a prime number, and 71 doesn't go into 160. So we are done with this one. Okay. Now, before I let you guys, thank you, Ulysses. It does seem easy because I think part of the problem is that when we were taught how to do these a long time ago, we were probably taught in a more complicated way. I know I was. But it doesn't have to be so. Let me show you something here. If I take 3 over 5 plus, let's say 2 over 7. If your denominators are, here is a fancy phrase for you. If your denominators are relatively prime. Now, the phrase relatively prime means that between these two guys, the only factor they have in common is 1. That makes them relatively prime. Up above, 32 and 40, they had a common factor of 8. So they weren't relatively prime. But if your denominators are relatively prime, the quick, easy way of working this out is to take this denominator and multiply it in both the numerator and denominator like this. Take this denominator and multiply it here for the other fraction. Now, I know, and I've had students that have told me this before, there is a very quick, easy way to get a common denominator, but it's not necessarily going to be the least common denominator. And that's by taking these two guys right here and multiplying them. Okay? If you multiply 32 times 40, that will give you a common denominator. It won't be the least common denominator, and there will be a lot more simplifying you have to do, but it will be a common denominator. Here, since 5 and 7 are relatively prime, if you multiply them, that is your common denominator. So when I work this out, I get 21 over 35 and 10 over 35. Okay? Which, when you combine, you get 31 over 35, just like that. Is it still blurry, Kevin? And if you say it goes blurry, is everything going blurry, or is it just the writing? Is it the webcam? Because I'm thinking if the whole thing is going blurry, that's going to be an issue with bandwidth and not with the devices I'm using. Now, we'll let you guys know that I am recording this, so... Oh, the writing. Well, is it okay now, or is it still blurry? At any rate, I'm hoping that I can upload this to my YouTube channel so you guys can view it again later or share with other people. Okay, good. It's back to being good. I did order a new document camera, so I'm hoping that works out. I really wanted to grab the one that was in the classroom, but since IT wasn't available to check out equipment, I couldn't take it. It's such a good one. I tried to see how much it was online, but I don't have that. I don't have that kind of money. Oh, you all right, girl? Sorry. So let's see if I give you one. See what you guys can do with it. I'm going to take. Oh, I probably shouldn't do this. I feel like I'm being mean. And let's do. There we go. 23 over 44 minus 17 over 55. Why don't you guys take a moment and see what you guys can come up with it. Now, I suggest you do what we've done in the past couple of problems. Identify a common factor for those denominators. I knew someone was going to say that. Come here, girl. Excuse me. I know. Come here. Ugh. I know. I know. Now you want to eat me, don't you? So, for those of you who've heard me talk about, no, don't bite me. I know. Oh, right in the mouth. Why do you go for the mouth? All right. I think she's had about enough. Oh. Good night. Yeah, I think I might have got my dog a little bit too excited because now she wants to bite everything. They're going to have a little tug of war later because that's what she likes. All right. So did you guys find the common factor for those denominators, or were you just staring at the dog? What? All right. Now you guys see. Let's see if you're right, Ulysses. 11. Yes. Thank you. Okay, so two people are saying 47 over 220. So if two people say the same thing, it has to be right, right? All right, so the common factor here is 11. So this is 11 times 4 and 11 times 5. So these guys are already the same. Put in the missing factors here. I promise I'm not trying to make these numbers all the same. It's just kind of ending up that way. So this guy's missing the factor of 5 in both the numerator and denominator. And this is missing the common factor, or the missing factor of 4. All right. So whether you do 45 times 5 or 55 times 4, you get 220. 23 times 5 is 115. Oops. Wait a minute. Yeah. 17 times 4 is 68. Right? Everybody's good with that? And so when you do the subtraction here, again, keeping the denominator the same because we worked hard to get it to be the same denominator, 115 minus 68, 47. Now this does not reduce. It stays as it is. 47 is prime. And if you were playing around on a calculator and you just want to verify the way you have is right, again, you're not using the calculator to do your work. It's just there to check. Okay. So what do we have here? So 23 divided by 44 minus 17 divided by 55. Now, understand that the calculator is going to follow the order of operations it understands with the division. These guys are already connected to each other. There's my crazy decimal. Again, that doesn't mean a whole lot to me. I can convert this guy to a fraction in the calculator, or I could just type this fraction in to see if it gives me the same thing. So math, convert to a fraction, 47 over 220. Too easy. It was too easy. This can't go on forever. 7 over 12 plus 5 over 18 minus 3. What was I thinking of? Three over 16. Are you proud of yourself? This is what you wanted, isn't it? So see, now you have 3 denominators. You've got to find that common denominator for all of these guys. Now, one thing you can do is that you could just do a pair of them at a time. So if you work on just these 2 guys right here, you can find that common factor, and then we'll come back and we'll bring the 3 over 16 in a moment. 2. Well, the common factor for 12 and 18 would be 6. But we're going to do it this way. So let's do 6 times 2 and 6 times 3. And again, I'm going to come back to that guy. So if I do this, where these guys already have the same factor of 6, this one's missing a 3. And this guy is missing a factor of 2. So when I put these guys together, we get 21 over 36 plus 10 over 36, right? 144 is the LCD? Maybe. Let's see what happens. All right, so let's bring in that third fraction to make sure that everybody's on the same path here. These guys are already the same. So in the next step, if I make any adjustment to one, I'll make the adjustment to the other guy too, so they would still have the same denominator. Let's just focus on these 2 guys since they're right next to each other. The common factor for 36 and 16 is 4. So this is 4 times 9, and 16 is 4 times 4. And you see right here that these guys have the 4 in common. And to make sure everything else balances out, this guy's missing the factor of 4. So do that. And this guy's missing the factor of 9. Now if I stop right here, you're going to see that these 2 guys are going to have the same denominator. 4 times 9 times 4. They have the exact same 3 factors. But remember, I said that if I make an adjustment to this fraction, I need to do the same thing over here, since these guys were already the same, had the same denominator. Okay? All right, so what does this give me here? 21 times 4 is 84, and 36 times 4 is 144. Thank you, Tone. In the middle guy, we have 40 over 144 minus, and 9 times 3 is 27, again, over 144. We're doing this so that we have the same denominator. So if something happens where the denominators are no longer the same, you've made a mistake somewhere. All right, so when I put all of this together, let's see if I can make this easy on myself. You know, I'm just going to go off here to the side. All right, so 84 and 40 is 124. And then I do 124 minus 27. So we get 97. So altogether, 97 over 144. 97 is another one of those prime numbers, so we can't do anything with it. So there we are. That's it. Now that one did take a few more steps, but I hope you can see logically, piece by piece, how we do this. You could look to identify the LCD for everything at the very beginning, but I'm going to tell you right now that it can be quite cumbersome. But there are different ways of working this out. Now, one of the ways they would have shown you a long time ago is they say, okay, let's take 12 and let's write out multiples of 12. 12, 24, 36, 48, and so on. You do the same thing with 18. Find multiples of 18 and let those guys just keep on going. And they would say do the same thing with 16. Find the multiples of 16 like that. And what you would do is that you would look for the number that they all have in common that's the smallest. But it's going to take a while to get there. Another way of looking at this is that you could find the common denominator between these two guys, which is what we did at the beginning, 36. And then you start looking at this. Does 16 go into 36? No. So you build off of multiples from there until you get to one that does, right? So let's take that. I'm going to start with the largest denominator here, 18. All right, does 12 go into 18? The answer is no. So I got to go to the next multiple of 18, which is 36. Does 12 go into 36? The answer is yes. Okay, so that's a good start. So I know that 36 is common for both of these guys. Then I look at the 16. Does 16 go into 36? Not evenly. So now you're working on the 36. 72. Does 16 go into 72 evenly? No. The next multiple of 36 is 108. That doesn't work. And then you get to 144, and finally you would get to a common denominator, a common multiple for all of those guys. So you would have to figure out, okay, 12 goes into 144 how many times, and do the same thing for 18 and 16. But it doesn't really matter what you do, the LCD is going to be 144. Okay. Well, we've been doing this for an hour and 20 minutes. I want to thank you guys that showed up. Thank you for stopping by. Even though I don't get to see your faces, thanks for the comments. Thanks for the chat, for following along. I think what I want to do for my next stream is something related to factoring. Because you know how much I love to do factoring. And you also know how important that's going to be for this upcoming test. So we're going to do some of the basics with factoring, starting with factoring by grouping. We'll review the AC method. And I'm also going to try to show you guys some other factoring techniques that I haven't shown you in class because we haven't had time for that. And there'll be a lot of time for you to participate and come up with some answers on your own. Okay. So thank you guys for finding me here. Remember, you can find me pretty much anywhere just with that username, mathman24. And as I mentioned earlier, I am recording this, so I'm going to do my best to upload that to YouTube. There's a URL for you. You can also, again, follow me on Twitter, and of course here on Twitch. Again, most of the time, it's probably just going to be doing math. I might do some video game stuff. It just depends. Like I ever have free time, right? Okay, those are the best ways to find me. Oh, YouTube videos to watch. Yeah, just keep going with the college algebra stuff. I'm not sure exactly where we... Let me look at that real quick. I can't remember what video we would have been on right now, but again, some of those videos are about 7 years old, so I want to update those big time. So I'm going to be doing that over these next few weeks. Alright, so the last thing that we had before we went on break, we were talking about piecewise defined functions. So if you start at video 100, watch those guys. I'm going to try to make some new piecewise defined function videos and just kind of we'll build from there. So look for new uploads. I would say like and subscribe, but that's just not me. So thanks guys for stopping by. Hope you have a great evening, a good weekend. Stay safe, be smart. Again, before you do anything, think, what would Mr. Craig do? All right, I'm out.